Wave interactions. So at the end of the Slinky lab, you were playing with sending 2 or more pulses down the length of the Slinky to see what happens. When you have a pulse that creates a wave that travels down a medium, and that wave reflects off a boundary at the other end, and then interacts with another wave that was on in the same medium, we say that those 2 waves are in superposition with each other, meaning both those waves have interacted with each other either positively or negatively, constructively or destructively. So 2 types of interference, once again. Constructive interference, you have pulses on the same side of the equilibrium line that interfere with each other. And when they superposition, the amplitude will be the sum of both the waves. So if I send the red pulse down the length of the Slinky, and then another pulse is on the same side of the Slinky but going on the opposite direction, when those 2 amplitudes intersect with each other or superposition, the amplitude will be the sum of the 2 parts. So the red one plus the blue one will equal the black one. Destructive interference is the exact opposite. Suppose you have 2 pulses, one on the top of the equilibrium line, one at the bottom of the equilibrium line. When those 2 waves intersect with each other or superposition, you still add up the sums of the amplitudes. However, if the waves have the same amplitude, those amplitudes will cancel each other out. And so momentarily, it will look like the wave has disappeared. However, over time, that wave will reappear after the 2 waves have passed each other. Really important to note here that waves don't start and stop as they are traveling down the length of a medium. They will pass right through each other because waves, remember, transfer energy and not particles. Let's take a look at a slow motion wave generator and look at constructive versus destructive interference. So what you will see here is 2 people creating a wave, and the first slow-mo is of destructive interference. Wave 1, wave 2 intersect, and when they intersect, temporarily it looks like there's no wave, but wave 2 just passes by wave 1. Constructive, exact opposite. The 2 amplitudes add together, you make a bigger wave, and then the 2 waves pass each other. Looking at this in slow-mo. So how does the boundary affect how amplitudes either cause constructive interference or destructive interference? This really does depend on the type of boundary that is on the other end of the medium. We're going to take a look at a couple of these with our PhET animation. So for the first one, I'm going to have a fixed end, meaning that this clamp, the C clamp, is not going to move up and down. And I'm going to send 1 pulse in slow motion and watch what happens to the amplitude as it travels down the medium, the string, and then back up. Notice it's on the top side of the equilibrium line, and then it's on the bottom side of the equilibrium line. So if you have a fixed end, that wave will be reflected off the boundary and return on the opposite side of the equilibrium line. Now let's change this to a loose end and do the same thing. Notice that the amplitude stays on the same side of the equilibrium line. So the reflection does not change when you bounce back again until you get to the other end. And then, of course, then there's the last type of boundary where there is no end, no boundary whatsoever. And what happens is that wave is just going to, whoa, energy goes straight out the window, and there goes the energy, no more energy on that string. Now, why is all of this important? We are leading to learning about sound, and sound is created by the creation of standing waves. And standing waves happen to be musician's best friend because we create standing waves inside musical instruments in order to create sounds that are unique to those instruments. So a standing wave is created when two waves of the same special frequency, wavelength, and amplitude travel in opposite directions and interfere or superposition themselves upon each other. There is a video that is attached to this Schoology page that will show a great example of standing wave motion. Please watch this video and then come back to my video. So in the video, you saw standing waves being generated at different frequencies dependent upon the wavelengths and frequencies generated by the speaker. So what I'm going to show you is standing waves with two fixed ends. First and foremost, and these are the same waves that you just saw in the video, first and foremost, let's remember what a wave looks like. A wave looks like from equilibrium to one maximum, from equilibrium to one minimum, and one back again. That is one wavelength. So if I consider the length of the string capital letter L, there are, in this particular picture, 1, 2, 3, 4 different what we call harmonics that can form standing waves. The first one here, you'll see that the wavelength, you don't have a complete one. You have half of one. You have only from equilibrium to a maximum and back to equilibrium. That means I can say that the wavelength is going to equal 2 times the length of the entire string. And that is due to the fact that in the length of the string, I only have half a wavelength. So the relationship between the wavelength and the string in this case is half. Now, for the second standing wave, the second harmonic, you've got a full wavelength. One up, back to equilibrium, one minimum, and then back to equilibrium again. So in the second harmonic, the wavelength is going to equal the length of the string, or in this case, they kind of mean the same thing. In the third harmonic, what you will see here is that you have, get my color here, 1.5 wavelengths inside of the length of the string. 1.5 is 3.5 wavelengths equals the length of the string. Or I can say that 2/3 of the length of the string is going to be one wavelength. If I think about dividing this up into thirds, 1, 2, 3, one wavelength is 1/3, 2/3. And then the last one, the fourth harmonic, when you've got two fixed ends, is you've got 1, 2 wavelengths for the length of the string. So 2 wavelengths in the length. Or I can go ahead and say that a wavelength is going to be half the length of the string. We're going to play around with this on another animation here. So what we have here is an animation that is going to show different harmonics for standing waves. I'm going to pause this at particular points to show you what's going on. First and foremost, I've got two waves, an orange wave and a blue wave, that are going to superposition themselves on each other. And when they do, there will be points of constructive interference and destructive interference. So I'll play that part in real time. You'll see them constructively interfere and destructively interfere at particular points. Let's move this to slow-mo. And when I move this to slow-mo, I'm going to put on top of that the standing wave that is formed. Now I'm going to pause it at particular points here, right here. So at this point, the blue wave has superpositioned itself on top of the orange wave, and you've got constructive interference or a larger amplitude on the top side of the equilibrium line. Likewise, down here, you've got the orange wave that has superpositioned itself on top of the blue wave, and it also has constructively interfered on the bottom side of the equilibrium line. And then as we keep going, slowly we will see some destructive interference occur right there. So at this point, the blue wave has destructively interfered with the orange wave because one amplitude is on one side, the other amplitude is on the other side, and so temporarily it looks as if there is no wave present. And that has happened here and here as well. And then when I turn this back on, I'll get a point of constructive interference again. And so when I go to fast motion, the green line will look like it's staying in one spot, even though the orange and blue waves are superpositioning each other to cause constructive and destructive interference. That is how a standing wave works. If I move this on to the third harmonic, that green wave looks like it's staying in spots due to constructive and destructive interference, and there's the fourth harmonic. This animation is attached to your Schoology page as well, so you can play around with that as well. There are two last definitions to give you in this video: node and antinode. Anytime that you have destructive interference where it looks like a wave is not present, you've got what's called a node. So in your first harmonic, you've got a node here, and you've got a node here. An antinode happens when you've got constructive interference. And so an antinode will occur in the first harmonic here. So an antinode. So in the first harmonic, I got two nodes, one antinode. In the second harmonic, I've got 1, 2, 3 nodes, 1, 2 antinodes. Third harmonic, 1, 2, 3, 4 nodes, 1, 2, 3 antinodes. And you can keep seeing the pattern here. Node, 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 and antinode, 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 antinode. Constructive interference, antinode. Destructive interference, node. You are now prepared to do the following problems. Page 394, 1 through 5, 398, numbers 36 through 39. I do not believe there's hardly any math involved in these, so we will be stamping these off on Monday. Thank you very much. Have a